Today we are going to be talking about analyzing functions, both algebraically and graphically, and also we'll talk about analyzing a function in terms of determining its domain. So first, let's talk about how we algebraically test whether or not something is a function. So remember that a function is a relation where each x value can only have one y value. Now, in order to algebraically test to see if something is a function or not, you want to first solve for y, and then once you've solved for y, you want to determine if the values of y are unique. In other words, one way to check to see is to see if there's a plus or minus. That's not the only case in which you do not have values of y that are unique. Sometimes it may have to do with having absolute value symbols in there. But essentially you want to see if I plug in any value for x, will I only have one value for y? Let's take a look at an example. So x squared plus y equals 1. To determine whether or not this is a function, we want to start by solving for y. So let's move the x squared over to the other side. And now you want to ask yourself, are the y values unique here? In other words, if I plug in a value for x, is there any way for me to get multiple values of y? You can try this out and see, okay, if I plug in a positive number in there, do I only get one y value? If I plug a negative number in there, do I only get one y value? In this case, yes, the y values are unique, and if you know the y values are unique, that must mean that this is a function. Let's look at the next example. It's almost the same as the last one. We have negative x plus y squared equals 1. Okay, so we'll start the same way. We'll try to get y by itself. So we'll add x over to the other side, and then take the square root of both sides. Don't forget that ends up being a plus or minus the square root of 1 plus x. And then you have to ask yourself, are the y values going to be unique here? Well, let's say I plug in x equals 3. Then I get the square root of 4, which is 2, but y will be equal to plus or minus 2. That means that when x equals 3, there are two different values for y, positive 2 and negative 2. So in this case, the y values are not unique, so we would say this is not a function. So that's how you would algebraically see whether or not something's a function or not. Get y by itself, and then test to see what happens with my y value. Do I have multiple y values, or do I have a unique y value? So now let's look at graphically testing to see whether or not it's a function. So you might remember the vertical line test. And just as a reminder of how the vertical line test works, if there's no vertical line that can be drawn such that it crosses the graph more than once, then it is a function. However, if you can find at least one vertical line to be drawn through the graph where it crosses the graph more than once, then it is not a function. Okay, so here in this first one, we can see that if we went through the entire graph with a vertical line, there's no vertical line that I can draw that will cross the graph in more than one place in one vertical line. So this is a function. In the second one, we can see that if you draw a vertical line anywhere on the right-hand side of the graph, so anywhere past that leftmost point, if you draw a vertical line, it's going to cross the graph more than once. So this one is not a function. And you can see how this relates back to the algebraic test for a function. In that second graph, you can see that, for example, 2, 2 is a point, and 2, negative 2 is a point. Right, so there are two y values for that one x value. Okay, so now let's talk about how you find the domain of a function. So there are two main things that you want to look out for when you're determining the domain. In general, the domain of a function is going to be all real values of x except for 1, anything that makes a denominator equal to 0, and or, depending on how many things you may or may not have, anything that makes an even radicand negative. Now, even radicand, this just means any sort of root that's an even root. So you may have learned it before in the past as you're looking up for square roots, which is true, but a fourth root, if there's a negative under that, that also would not work. So any even radical is going to be something you want to look out for. All right, let's take a look at a couple of examples. F of x equals negative 3x squared plus 4x plus 5. So the default is always all real numbers, but you want to look out for those two exceptions. So are there any denominators? No. Are there any even radicands? No. So in this case, the domain is going to be all real numbers. Let's look at the next example. F of x equals 1 over x plus 5. Do we have any denominators? Yes. Okay, so what did we say about denominators? You cannot have a 0 in the denominator. So you have to determine what value of x would make the denominator equal 0. So what we can do is we can just set x plus 5 equal to 0 and say it cannot equal 0 and solve for x. So x cannot equal negative 5. All right, so we checked for denominators. We know that x cannot equal negative 5. Now we also have to check, are there any even radicands? No. So our only restriction here is coming from that denominator. So normally the domain is all real numbers, but now we have a restriction where x cannot equal negative 5. So all real numbers except for negative 5. Now in interval notation, that would be everything from negative infinity to negative 5. Don't include negative 5, so parentheses, no square brackets there. And then anything from negative 5 all the way up to infinity, again, don't include negative 5. And that is our domain. Okay, our last example today. F of x equals the square root of 2x minus 3 all over 20x squared plus 11x minus 3. So again, normally we would say all real numbers, but look out for the two things. Any denominators? Yes, we absolutely have a denominator here. All right, so that 20x squared plus 11x minus 3 cannot equal 0. We are going to have to figure out what values of x would make that 0. So this looks like something we might want to factor and possibly split the middle in order to factor. So 20 times negative 3 is negative 60. You're finding two factors of negative 60 that will add to 11 and split the middle. Do all that. We should end up with 5x minus 1, 4x plus 3, which means that x cannot be equal to 1/5 or negative 3/4. Okay, so both of those values will make the denominator equal 0. All right, we checked for denominators. Now we check for even radicands. So in this case, we do have a square root in the numerator. So what do we do about that? Well, what was it that was restrictive about even radicands? It's that we can't have a negative number under an even radicand. Okay, so because the square root of 0 is equal to 0, the only restrictions that we have are that this cannot be negative. This 2x minus 3 cannot be negative. In other words, this expression under the square root must be greater than or equal to 0. So that's what I'm going to write down. 2x minus 3 is greater than or equal to 0. All right, so now we can go ahead and solve this, and we find that x must be greater than or equal to 3/2. And now for our domain, we can write all of this out. So all real numbers except for 1/5 and negative 3/4, and it also has to be greater than or equal to 3/2. Now combining that together, if x is greater than or equal to 3/2, which is 1.5, then think about 1/5. 1/5 is smaller than 1.5, and negative 3/4 is also smaller than 3/2. So even in putting both of these together, we can actually simply say that the domain is going to be all real numbers greater than or equal to 3/2. And we can just say from 3/2 to infinity, with square brackets on 3/2 when we write this in interval notation, and we don't have to worry about the 1/5 and the -3/4 because neither of those are in that interval.